All right, you Rocketeers, you Maverick Renegades, let's do this. Here's our rocket lab. I want to show you a little bit about potential, kinetic energy, and forces here. Remember, these are old chapters, but I think just going over this would be really good. Remember, look at these charts here. These are all mechanical energy. These are all like the distribution of mechanical energy and mechanical energy. Mechanical energy is split up into either some sort of potential energy and whatever movement energy or kinetic energy is in the system. Okay, these two adding up together will be the total energy, which we call mechanical. So look here, when your rocket first is about to lift off at ground zero, T minus 5, 4, 3, 2, it goes up in the air in the beginning, it's 100% kinetic energy, right? So right here, this would zero out, right? Our potential energy would zero out, and our mechanical energy would be all composed of kinetic energy, okay? As it goes up, it's gaining height, so look what happens. This kinetic energy is going to decrease and all become gravitational potential energy, right? Which means if I were to let go of it up here, it would drop to the ground and convert back to kinetic energy. We don't lose energy in the universe. It's either converted into some other form of energy or as work, right? Like if I drag a box across the ground, or if I drag a box across the ground over here, right? So I drag a box on the floor. It's the potential energy in my chemicals, in my muscles, gets converted into work in the box, but it doesn't 100% get converted into there because it drags on the floor. There's friction and there'd be heat, so some of that energy is lost. I wouldn't ever get 100% of my energy converted. That'd be really nice. The only type of conversions that work like that are going to be like your matter and antimatter collisions, right? You get almost 100% energy efficiency there. It's really nice. Okay, so anyways, so let's look here. All right. So it goes up, becomes gravitational potential energy, and as it falls back down, it's decreasing. But at every single instant, notice that these bars never get higher if you were to add them up, right? So any intermediate position here would never be able to add up to the height of the original kinetic energy. Okay, so this has some pretty important ramifications when we start doing mathematics. So let's look down here. Let's look at a free body diagram of our rocket going through the air. Of course, I use little orbs, but I'm lazy. So the beginning, when it's at rest, right, we have no kinetic energy at all. So right now, what this is, the two forces that I would have acting on it would be gravity pulling down, but since it's not accelerating downward, we know there has to be a balanced force pointing upward, right? So remember that since this is perpendicular to the surface, remember, anything that is perpendicular to the surface, we have another word for it, starts with a norm, ends in O. It's normal force, right? Normal force. And when it goes up in the air, we've traditionally thought of it as gravity going down and some sort of applied force going upward. In this case, it's thrust or force thrust. But you know that in the real world, we have another force that's acting downward, right? Because our rocket doesn't quite go up the same way that it comes down, right? And this is force air drag, right? So let's look at our kinetic energy equation, right? At the beginning, we can look at our energy as 1/2 mv squared, the mass times the velocity squared of the rocket, and then divided by 2 will get us our kinetic energy. At the very top, we know that all of our kinetic energy, remember all of our kinetic energy here, same height as gravitational potential. So whatever value we got for kinetic energy at the beginning, we could get at the end, right? We could plug this number into here, right? So we could basically say our kinetic energy max is equal to our potential energy max. It's old stuff, right? Hopefully this is just jogging your memory. And since these two values are equal, guess what we can do? We can get the equation for potential energy, mgh, and equal it to 1/2 mv squared. Cool, right? And of course we're starting with this because we're using the time from your video. We're plugging it into the distance or height equation, the distance vertical, and that was 1/2 gt squared. You know that g on Earth is 9.8. We've been using 10 meters per second squared. It's acceleration. But for this, since it's real world, we wanted to use the real world value, 1/2 gt squared. We're going to take this height, plug it into here, take your mass that we're going to use with the scale that one of our wonderful chemistry teachers lent us. Okay? And we're going to take this, and we already know the value of g, and then we'll go ahead and just solve for, hold on real quick, the pen is messing up. All right. What would one of these tutorials be without all of my technology messing up? Okay? We're going to multiply by 2 to get rid of this 1/2, right? So mv, uh-oh. I have to do this by hand. Sorry, guys. Okay, mv squared, really racing to the finish line here, huh? mv squared, let's try it again. Okay, equals mgh times 2, right? Because we moved the 2 over here. And we're divided by m, and guess what? The m for kinetic energy is the same as the m for gravitational potential energy. So guess what? I don't even have to give you. You really don't need the math, so we're not going to do that. Okay, so v squared, sorry we didn't need the scale, okay, equals 2gh. And then we can, how do we get rid of a square? Do the square root, right? So our velocity initial, so we're going to figure out the velocity by taking the square root of 2 times, don't do this to me. No. My last one. I'm having to reset my pen every time, guys. 2 2gh, you get the point. 2 times gravity times height and takes the square root of that. All right, so look at this little trick right here, because if you do AP physics, this is something that's very common. A lot of the times you'll have 2 or 3 missing variables, and just by writing out the equations first, which I've always told you to do in this class, you can cancel out variables that you don't even need, as long as you keep track of what these m stand for. These aren't different masses, right? The rocket had the same mass at the beginning as the end. We're not counting the rocket fuel, because your rocket jettisons all of its fuel like as soon as the cork pops. You have a good day, have a good summer, and finish this, get 100 on this. Bye-bye.